In this video, I'll show you how to solve the ALEKS problem called calculating average molecular speed. The equation that we're going to use to solve this problem is V equals the square root of 3kt over m. In this equation, V is the velocity or the speed of the gas or the atom, and that is going to be in units of meters per second. M is the mass of a single atom, so we're going to have to be careful with that. The mass of one atom, and that needs to be in units of kilograms. T is the temperature, and that needs to be in units of Kelvin. And this lowercase k is a constant called the Boltzmann constant, and it is 1.38 times 10 to the negative 23. And its units, it could be written in a couple different ways. It could be written in units of joules per Kelvin, but I think that it is more useful if we write the units as kilograms meters squared over second squared times Kelvin. I'm just going to move this down to make it easier to read. And so all that we need to do for this problem, it's actually pretty straightforward once you know the equation. All we need to do is plug in the value of the temperature, which is going to be given to us in the problem. And of course, it's giving it to us in Celsius, so we're going to have to do a unit conversion. And then we're also going to have to plug in the mass of the atom. Every problem that I'm looking at is giving you a slightly different atom. This particular problem is having me calculate this for argon. I went ahead and looked up the molar mass of argon, got it copied down right there. If you don't have argon, you're going to need to look up the molar mass of whatever atom you do have. So we do have to do a little bit of conversion. First of all, we need to convert our temperature from Celsius into Kelvin. Let's just go ahead and start with that. To convert from Celsius to Kelvin, we're just going to add 273. So the temperature in Kelvin is going to be our temperature in Celsius, which is negative 25, and then we're going to add 273.15. That's going to give us that conversion. Negative 25 plus 273.15 gives us a temperature of 248.15 Kelvin. So we're ready to plug that in. And then the other thing we need to calculate is the mass of a single atom. So we're not using the mass of a mole of atoms. We're using the mass of a single atom. We do need to do a little bit of conversion there. What we have for argon, we have 39.948 grams per mole. And this is the number that's coming off of the periodic table. So whatever gas you have or whatever atom you have, make sure you're looking up its molar mass from the periodic table. And then we're going to multiply that by a conversion factor. We want to get rid of that units of the unit of mole, and we want to convert into just a single atom. And that relationship between moles and really anything is Avogadro's number. 1 mole of whatever we're talking about, I've got to give myself some more room here, is equal to 6.022 times 10 to the 23rd. In this case, we're talking about atoms, and the mole units are going to cancel out. So this is going to give us the mass of just a single atom, the grams per atom instead of the grams per mole. And I'm going to need to use the calculator for that. 39.948 divided by 6.022 times 10 to the 23rd. And that is going to give me a mass of 6.6337 times 10 to the negative 23. That is grams per atom. I'm not going to continue to write per atom because in this equation, mass is asking for the mass of an atom, and that's it right there. We do need to be a little bit careful here. This is asking for the mass in units of kilograms. I just calculated the mass in units of grams. So I do need to do one more conversion to go from grams to kilograms, and I'll write that one out. 6.6337 times 10 to the negative 23rd grams. We want to cancel out the units of grams, convert into units of kilograms. Kilo is the prefix that represents 10 to the 3. So 1 kilogram is 10 to the 3rd grams. And to do this calculation, we're just going to take that answer and we are going to divide it by 10 to the 3. And that's going to give us 6.626 times 10 to the negative 26 kilograms. Squeeze that in there. All right, so we're ready to plug everything into this equation. Notice that ALEKS gave us some information that we don't need to solve this problem. It gave us the pressure. The speed of a gas has nothing to do with the pressure. It's just based completely on the temperature and then the actual, the mass of the gas or the substance itself. So we're ready to plug everything into this equation. The velocity or the speed of the gas, this particular gas is going to be the square root of 3 times that constant 1.38 times 10 to the negative 23rd kilograms meters squared over second squared times Kelvin, multiplied by the temperature in Kelvin, which I calculated up here, 248.15 Kelvin, and divide by the mass of a single atom of the gas in units of kilograms, 6.6. What did I write this for? 6.6337. I just had Avogadro's number on the brain. 6.6337 times 10 to the negative 26 kilograms. We can take a look at how our units are canceling. The kilograms are going to cancel. Kelvin will cancel. We're going to end up with units of meters squared over second squared, but then we're going to square root that. So we're going to end up with units of meters per second, which is perfect. Okay, so we're ready to plug stuff in. We've got the square root of 3 times 1.38 times 10 to the negative 23rd. There's that constant times our temperature, 248.15. And then we are going to divide all of that by that mass in kilograms. And that gives me, don't forget our square rooting this, that gives me the square root of 206.5. Units are meters squared per second squared. And that was this. Forgot that I put the square root function in there. 206.5 meters per second. That's pretty quick. ALEKS wants this to 3 significant figures, so that's going to be 207 meters per second, and that's a pretty reasonable answer for this particular problem.